In this unit, we're going to look at inverse functions, and specifically we're going to be looking at the trigonometric ones. But first, let's just revise inverse relations, and then we can look at how we turn them into functions by restricting the domain, and then we can move into how we can apply it to trigonometry. Now, we have already seen inverse relations back in Chapter 5. So if this quick recap doesn't really make sense, go all the way back to the original lesson in Chapter 5 and watch those videos first. So a quick recap, if we want to create an inverse relation from the original, we switch the x and the y in the formula. If we can, we rearrange the formula in terms of y, so we get the y by itself and all the x's on the other side. I've written if you can because sometimes you've got a formula that's so complicated it's really hard to rearrange, and you wouldn't be expected to do that in this course. If it's a simple one, something linear, something that can easily be adjusted, perhaps you might need to complete the square, then you could be asked to rearrange it in terms of y, and that's normal to do that. Now we know that the original function or relation and its inverse are basically a reflection of each other around this line y equals x. So graphically, if you have already got a picture of a relation of some sort, you can find its inverse just by drawing it and using those art skills. It can be useful to turn your paper on the side so that you've got this line actually vertical, and then you can basically make it like a butterfly painting, making things the same on both sides. So potentially you should be able to sketch an inverse relation from an original, even if you don't know the formula for it, just by using those art skills. So that's handy to know. Now, the domain and the range of a function or a relation and its inverse are literally swapped. And that's because the domain of one becomes the range of the other and vice versa. So a classic one that we've already seen here, which is a nice little bit of revision, we've got the graph here of y equals e to the power of x, so a basic exponential curve, and we can see here that its inverse relation is y equals log with a base e of x. Now we can see graphically that they are reflections around the line y equals x, and we can prove algebraically that they are inverse relations of each other. If we take either one, let's start with this one, and we start by just switching the x and the y, so we'll write x equals e to the power of y. Then if we write it in terms of y, we could rewrite this as a log and say e to the power of y equals x, and now we have, of course, the formula for this one. Similarly, we could start with that one, and we could say, let's switch it so that we have the log of y is equal to x, and then of course we can rewrite that as an exponential and say that's the same thing as e to the power of x equals y, and we've gone back again. Now so far I've used the word relation instead of function, because if you'll remember, a relation is anything that you can graph on a Cartesian plane, whereas a function is a very specific relation. It's a special one that passes the vertical line test. Now we've seen this way back at the start of year 11, but it's a good reminder to look at it again. Passing a vertical line test means that a vertical line only goes through it once. Okay, so we've learned how to look at our different types of relations. We've got ones that are one-to-one, and remember this means 1x for every 1y. In each case here, you can remember these by thinking many x's to 1y. That would be something like a parabola, say, where you can have two x values that both have the same y partner. One to many is 1x to many y's, so you get that if you had something like a sideways parabola where one x value has two y partners, and many to many would be something like a circle where you've got multiple failings of the vertical line and the horizontal line test. Now we've already considered that when we make an inverse relation from some original graph, we're switching the x and the y values, and so we're also switching the domain and the range of each graph. So it makes sense then that if our new inverse is going to pass a vertical line test for it to be called a function, then the original really has to have passed a horizontal line test for that to work out. Now we've considered this before, so really this is revision. But let's have another look at which test, the horizontal or the vertical line test, each one of these would pass. Well, a one-to-one function is going to pass both. So it passes a vertical line test, it passes a horizontal line test, and so does its inverse. Okay. Many-to-one, that's something like our upright parabola. It passes a vertical line test, but it doesn't pass a horizontal line test because it's going to cut through it twice. Something that's one-to-many fails the vertical line test, so it's not a function, but it passes the horizontal line test. And this one fails both tests, so it's got nothing going for it in that way. Now we can see over here that if something's passed a vertical line test, then its inverse will pass a horizontal line test and vice versa. So we get this sort of situation. Now, if something does pass the vertical line test once you've made the inverse, we can say that it is a function. And so we've clearly got a function here, and we've got a function here. The interesting thing about this one is that its original wasn't a function, but the inverse is. Now, if both the original and the inverse are both functions, that's when we can use that special notation y equals the inverse function of x, and we write that like that. We need to be really careful that we don't confuse that with a reciprocal function. A reciprocal function is where we might take the original function, some y equals f of x, and the reciprocal of that would be 1 over f of x, which is a very different thing. Now that can be written as f of x all raised to the power of minus 1. And see how that looks quite different from this one, where the negative 1 is put in here. So make sure we never get these confused. This is an inverse function, quite different from a reciprocal. Now if we have either of these two graphs, and we want them to be a function once we've created that inverse, then what we can do is restrict the domain, which is just really a nice little hack that we can use. We cut down the size of the original that we're using, and we say we'll just use this part, so that then when we find the inverse, it will pass a vertical line test and it will be a function. And if we do that, then we can use this notation for those types of graphs. Now we've seen this before, but let's revise it again. For inverse functions, the inverse function of a function is just x, and the function of an inverse function is x. Now this makes sense because when we put something through a function machine, we've got inputs, and if we put x in, then what we get out is the function of x. So this is an f of x machine. But what an inverse function is something that if we take what came out of this machine and put it back through this one, it makes sense that what we get is what we put into the other machine in the beginning. It's literally something that's going to spit back out whatever we put back in. So we can prove this algebraically. Let's just take a nice simple function. How about something like a nice easy straight line? And let's create the inverse by saying let's swap the x's and the y's. And now let's rearrange it so that the y is the subject. So if I subtract 1 from both sides and then divide both sides by 2, I'll get a y here, and I'll get half x minus a half. Now let's just graph these to consider, well, just to check really, that they do actually look like inverse functions of each other. This one's got a y-intercept of 1 and a gradient of 2, so it goes something like this, and this point here would be negative a half. And this one has a y-intercept of negative a half, and it's got a gradient of a half, so that's more like this, and this point here would be 1. Now you can see there on my quite dodgy sketch, it does look indeed like a reflection around that line y equals x. We can see there. So a nice little visual check that your algebra is looking right. Now let's prove these two things algebraically for these two functions. Now to do that, let's give them function notation. So this is our original function. Let's call it f of x. And this is our inverse of the original. So let's call it, with blue, the inverse function of x. Okay. And now we can verify this one here. Let's say the left-hand side is the inverse function of the function of x. And now let's start with these inner brackets. What's in there is just f of x, which is 2x plus 1. So let's write, we've got the inverse function of 2x plus 1, just replacing f of x for something it's equal to. And now what this really means is we need to sub 2x plus 1 into the inverse function. Wherever there's an x in it, and there's an x here, we're going to write 2x plus 1. So we say we've got 2x plus 1 over 2 minus a half. Now I can see here that my denominators are the same, so that means I've got 2x plus 1 minus 1 over 2, and the 1 minus 1 is going to go, so I've just got 2x divided by 2, which is x, and that clearly is equal to the right-hand side. So I've just proved this one. Let's have a go at proving the other one now. We can just change this around a little bit and say we're looking for the function of the inverse function. So here, what we really want is the function of, now what is the inverse function? It's this, isn't it? And what this means is take all of that and plug it into the original function. Anywhere there's an x, and here there's 1, and we've got 2 lots of some stuff plus 1, but this needs to be our stuff. So we put this in where the x is. So we've got 2 lots of x over 2 minus a half plus 1. Now we can expand the brackets, and 2 multiplied by that gives me x. 2 times negative a half plus 1, and clearly we get x as we sort of expected, should get x if it works out, and we've proven this little identity as well.